Spectrophotometry of copper compounds. That's your next lab, and we'll be going over that today in this video. The objective of this lab is to figure out which of 4 unknowns that you'll be given is which. So these are your options. All of the 4 are listed here. You just need to figure out which one is which. These will all be solids. Okay, so you'll get 4 different solids. They all contain copper. See that? They all contain copper, but they have different molecular masses, and they certainly have different properties. And you will use these properties and the amounts of copper in each to figure out which one is which. So that's your objective. So that means that really needs to be what your conclusion is, right? Which one's which. You'll be using something called percent mass, and you may or may not have learned this in lecture, but I'll go over what it is. Just a percent, right? Percent is the part that you're interested in divided by the whole times 100. So in this case, our percent by mass of a certain element in a formula is the mass of that element divided by the mass of the entire compound times 100. So for example, if you wanted to know the percent of iron in iron oxide, you would have the mass of the iron, okay, the mass of one atom of iron is 55.85, but we have 2 of them, so you have to multiply that by 2, divided by the entire molar mass of the iron oxide times 100%. So this gives us 69.94% of iron in this case, iron 3 oxide. We want to calculate the percent mass of copper in each of our 4 possible compounds. And this is the value that we will experimentally determine. We're going to experimentally determine the percent mass of copper, and we'll compare it to our knowns, because we know which of the 4 they are. We just don't know which one's which. So you will calculate the percent mass of copper in each. And you should do that really before you even come to lab. Make sure you include the mass of the water in the hydrates. You have 2 different hydrates in the total mass, so the total mass that you divide by. So for example, when you do this calculation, perhaps you would get something like a 25, 45, 67, and 68% mass for 4 compounds. And let's say you experimentally calculate, and I'm going to go into how we're getting those numbers, don't worry about it. How we're going to experimentally calculate these numbers. But let's just say we came to numbers like 22, 42, 68, and 70. Okay, so this is what we experimentally calculated. This is what we're comparing to. Okay, these are our knowns. So I could pretty accurately conclude that this material, whatever that one was, is probably this one. Right, and our 42 is probably the 45. But look at the 67 and 68, 68 and 70. Okay, those numbers are too close to really call. I'm not sure if this experiment, maybe this is unknown C. If this is unknown C, I'm not sure if it's this material or this material. Okay, so and that indeed is going to be what you run against. You will have 2 of your formulas will come out to be quite similar in percent mass. So you'll need to do something other than just determine percent mass to identify those last 2. But the percent mass will give you 2 of the 4. You'll need to perform some reactions with nitric acid and barium nitrate in order to determine the identities of the other 2, the 2 that are pretty close in percent mass. What you should do before you come to lab is predict the products of each of the 8 reactions. So you have a copper compound, and you can react it with nitric acid, figure out the products. React it with barium nitrate, figure out the products. Figure out the products using a double replacement or double displacement exchange reaction. And you've learned all that. So for example, for the copper carbonate, this is a solid, okay? If we add it to barium nitrate, do a double displacement, the metal replaces the metal, and you get copper nitrate, and that is aqueous. Barium carbonate, so your metal goes with your other nonmetal, Barium carbonate is a solid. So figure out what you expect to see. So from this, I would expect to see a precipitate being formed when copper carbonate is reacted. So if copper carbonate was one of the materials that I wasn't sure which one it was, I would know that at least it makes a precipitate when I add it to the barium. Okay? Others might be gas forming reactions. So do I expect to see bubbles? Do I expect to see a precipitate? And perform each of these 8 reactions. You will see what you get, okay, and then use that information to help you identify which one's which. You need both. You need the percent mass and the observations from these reactions to determine all 4. So that's where we're going. We are going to use something called spectroscopy to determine the percent copper in our samples. And what spectroscopy does is it takes a source of light and gets it into one wavelength of light and passes it through a sample and into a detector. Samples will, depending on what they are, will absorb light. And our sample, our copper sample, is going to absorb light at 800 nanometers. So our spectrophotometer will be set to 800 nanometers. And when we pass a beam of light through, depending on the concentration of this sample, a certain amount of that light will be absorbed. So we know the light, the amount of light that we pass through it, and this detector picks up the amount of light that passes through. So whatever's missing is what this sample picked up. We're going to use something called Beer's law to help us interpret that data. Beer's law tells us that the absorbance, okay, so that was the number that we got from the detector that says how much light was missing, how much was absorbed. So that absorbance is proportional to, so if one goes up, the other one goes up, the concentration in the solution. So this is going to give us information about how much is in the sample. If we plot absorbance versus concentration, we get a straight line. Okay, so this is a Beer's law plot. So in this case, we have 5 points, 1, 2, 3, 4, 5, of absorbance or concentration, and then how much light did it absorb. And this is proportional. These other 2 variables in here, so this, we talked about the absorbance, we talked about the concentration. These other 2 variables are constants. Okay? The molar extinction coefficient is just a number that's unique to each material. Okay? So our copper ions in solution will have a specific molar extinction coefficient. B is the length of the sample cell. So this is the length of the cuvette that we pass the light through, and that will stay constant throughout our entire experiment. So these 2 values are constants. So this is the absorbance equals some number times concentration. So since this always stays the same, okay, these are proportional. This looks an awful lot like a linear equation. Y, right, this is on the y-axis, equals the slope, okay, this number, both of these multiplied together, is just a number, it's a constant, and this is the slope of the line, m, right, y equals mx, x is the concentration, plus b. Looks like plus b is missing, but look what b is. B is the intercept, right? And b is 0, because we have 0 absorbance at 0 concentration. So from this plot, you can get the equation of this line. We call this a trend line. Okay? And here's our equation, y equals mx plus b. So what the value of this is, once we have this, we can take any sample, read its absorbance. So let's say my absorbance is here. If I know the equation of this line, I can have this y gives me this x. So we can solve for concentration if we have an absorbance. And that's exactly what we're going to do. Okay, so we have to make a standard plot for copper. We have to make that Beer's law plot. And how do we do that? This is right out of your lab, and you should have this data table in your lab notebook before you even come to lab. Okay. So we will have 4 points on our plot. So we have 4 points, standard number 1, 2, 3, and 4. And you will have, when you come into lab, you will see 2 burettes set up in the hood. One will have nitric acid in it, and one will have a copper standard in it. Standard just means that we know the concentration of it. Our copper standard will be 0.15 molar, 0.15 moles per liter of copper ion. And you will make 4 different cuvettes full of these standards. The first one we want to be just nitric acid. So you'll just fill the cuvette with nitric acid. That means we have no standard in there at all, no copper. The molarity of that then is 0. For standards number 2 and 3, you will use large test tubes, and right with the burette, you know where you start, you know where you're going to end to dispense 6 milliliters. So you'll add 6 milliliters of nitric and 4 milliliters from the neighboring burette that contains the copper. So you have a total of 10 milliliters in your test tube. Test tube for standard number 3 will be 3 and 7. So you don't need test tubes for standards 1 and 4. You can just bring your cuvette right over to the burette, fill number 1 up with nitric, fill number 4 up with your full standard. So for number 4, the concentration is exactly what the standard tells you that it is, 0.15 moles per liter. But you have to figure out and calculate the molarity of these mixtures that you just made in the 2 test tubes. It's really M1V1 equals M2V2. So we have the concentration of the original solution, which is your 0.15, times the volume of that standard that you used. And for standard number 2, that would be 4. If you're calculating standard number 3, that will be 7 milliliters. That then equals the concentration of your dilute solution. That's what you're solving for. That answer will go here and here. So the concentration of dilute solution times the total solution volume, and for both of those calculations, that total solution volume will be 10 milliliters, because you have, in the first case, 6 plus 4, and then 3 plus 7. So you could actually do this before you can come to lab, is figure out the molarity of these 2 standards. Then you can read your absorbance. So once you have your 4 cuvettes filled, you will go to the spectrophotometer, and there will be directions, and you will read the absorbance and write those in your data table in your notebook. After you get home, you don't have to do this in lab, but when you get home and you're writing up your report, you need to make a scatter plot in Excel. Please do not use a linear plot, because that will force your x-axis into a count, which will be 1, 2, 3, 4. That's not what you want. You want your x-axis to be 0, whatever these 2 numbers are, and then 0.15. You don't want it to be 1, 2, 3, 4. If it comes out to be 1, 2, 3, 4, then you know that you chose a linear plot instead of a scatter plot. Just redo it. So scatter plot in Excel, you will add a trend line to it. It'll give you that linear relationship. If it's not linear, then go back and recalculate those concentrations. And then ask Excel to display the equation. So the equation should be in y equals mx plus b format, and the b should be close to 0. Once you have the data for your standard plot, you need the data for your 4 unknowns. So you'll have 4 different copper compounds. You will measure a mass of each, and the mass is about 0.15 grams. It won't be exactly 0.15, and you should record to the maximum precision that the balance gives you. So if it gives you, 3 decimal places, then you use 3. And you'll record that mass in your data table here. You need to get all of that mass of all of the crystals into 4 test tubes, 4 different labeled test tubes. You have to keep track of which one's which. And then you will add 10 milliliters of nitric acid to each and dissolve. Okay, you can swirl it, you can use a glass stirring rod, make sure it's clean for each of the 4. Get all of that dissolved in 10 milliliters of nitric acid. You'll get that from the hood. You'll fill 4 cuvettes, just like you did for your standards, but these will then be your A through D unknowns. And on the spectrophotometer, you'll read the absorbance. So recall, When you get home, you have your standard plot. From these absorbances then, you can plug your unknown absorbance from your data table here. So for unknown A, I can take my absorbance and plug it in for Y. You have the slope, solve for X. That is your concentration in molarity. This table is also in your lab notebook or your lab manual. So the molarity of your copper ion is what you just solved for. So you can fill in this part of the table with the molarity, so that's X, that you just got from Y equals mx plus b. But how do you get then percent mass of copper? And I have that down here. Okay, so I have this part of what I'm showing you here. Moles per liter is what you just solved for. This is your X from your Y equals mx plus b. That is moles per liter of copper. Well, we had 10 milliliters total in that test tube. So if you multiply moles per liter times liter, you get moles of copper that were in that test tube. Moles of copper, so you'll have some number of moles of copper. If you multiply that by grams per mole of copper, and this is right out of the periodic table, 63.546 grams in 1 mole of copper. And multiply those together, moles cancel, you get grams of copper. That's your total grams of copper in that test tube. So if we divide, and again, remember, percent mass is the part over the whole times 100. So our part is our grams of copper divided by our total sample mass. This is the mass that you had, let's see, yep, right here. So from this table, this is the mass that you measured out, about 0.15 grams. That's your total sample mass times 100. That gives you your percent mass of copper. And recall, you are going to compare your percent mass of copper from your unknowns to your known percent masses of the 4 possible compounds. That information will give you the identity of 2 of the 4. You need more. You need to react each of your 4 compounds with nitric acid and barium nitrate. You're going to be looking for bubbles and you're going to be looking for precipitates. From those observations, you can then determine the identities of the final 2. So your conclusion should include the percent mass of copper for each of the unknowns, the identity of each of the unknowns, with a written rationale as to why you chose each one. Also include your percent error for your experimental percent mass compared to the percent mass that you calculated for the formula. Also include the sources of error. Please do not say human error, okay? So if you did something wrong and you know it, you should have just done it again. So don't say, well, I could have spilled some, well, did you spill some? If you did, then you should have redone it, okay? So that's not the type of error that we're looking for. Think about measurement, think about each of the steps, and even though you did your best, what could have been the error in that step or in that measurement. Okay, so that concludes our pre-lab video. Hope it's fun.